Hello, everyone, and thank you for joining us today. Welcome to the third session of our Cloud Evolution webinar series, which has been developed to explore the latest trends and innovations shaping the data center landscape that you need to be aware of in this era of great change. My name is Brian Baum, Corporate Marketing and Communications Manager at the Siemon Company, and I'm excited to be joined today by Gary Bernstein, Siemens Senior Director of Global Data Center Sales, and Ryan Harris, Siemens High-Speed Cable Assemblies Market Manager. As always with the Siemon Tech Talk, if you have any questions during the session, please enter them into the panel provided on the right-hand side, and we'll have a short Q&A session at the end to address them. Okay, Gary and Ryan, over to you guys.
Sounds good. Thank you, Brian. Appreciate it. I'm going to go ahead and share my screen here now. All right, Brian, are we able to see okay?
Yes.
All right. So thank you guys. Thank you everybody for attending today. I really appreciate it. Ryan and I are going to tag team on this and cover quite a bit of information, but hopefully this will be beneficial and educational to you guys. So with that, I'm going to just kind of kick things off. Starting out, we're just really going to cover a few primary topics. So just the AI market forecast, some of the technologies that are in there. Ryan's going to then jump in and talk in detail about some of the higher bandwidth requirements for these networks and applications. And then I'm going to close it out with the network considerations and impact to data center designs. So getting into the forecast and technologies a little bit, really, I just wanted to start, as Brian highlighted, I mean, we are really just in an era of great change. I mean, this is, representing a automation of some semiconductor chips, and really, this speaks to the fact that things have really changed, and it's really talking about moving from a CPU based computers to GPUs, so central processing units to graphical processing units. And all of the applications, and this has been coming and being in development for many years. There's been a lot of work with CPUs and GPUs and neural networks and machine learning for many years, and really just we've started seeing things come to light in the last couple years. So if I kind of go back and review some of the timeline a little bit and what's happened in the last year, it's pretty amazing. A little over a year ago in November, we saw OpenAI introduce ChatGPT, large language model, and that really kind of kicked off a flurry of different activities and events in the market. Then in March, Google and Microsoft followed up, with their solutions, Bard and Azure service. A couple other points I thought were relevant. Bill Gates referenced, and this is a quote from him back in March, AI is as revolutionary as mobile phones and the internet. Looking into, in May, Jensen, the CEO from NVIDIA, stated we have now reached the tipping point of a new computing era. And then really to end out the year, NVIDIA, who really has been the market leader so far in this space from a hardware standpoint, just kind of highlighting their results, in Q3, which is really kind of end of calendar year, was up almost 300% their revenue to $14 billion for the quarter. So there's been a lot of the product and hardware sold in the market, and so we're definitely seeing quite a bit of activity in terms of actual deployments in the marketplace. So with that, I kind of jump into what is Gen AI, and not to get into too deep of the weeds, but there really is really two different types and two different categories really of models, so training and inference. And this is, I took this from NVIDIA. It's really trying to explain this and show an example using recognizing dogs and cats. So, on the first side, the training, it's really utilizing a huge amount of existing data and creating a model. This is using deep learning, which is a type of machine learning, and neural network models So it really takes that data set and trains this model to recognize, right, whatever that is. In this case, they look at a lot of pictures and videos and everything of dogs and cats, so that model can recognize on its own the difference between a dog and a cat. So with that, the end result is kind of a trained model and a capability. Then the next phase of that goes to inference, which is really applying this same model into an application, a service, and solving a problem. In this case, it would look at a new piece of data and say, all right, that is a dog, and it's this type of dog, and so forth. So that's really kind of the two different categories, I guess, of models and application. So far, a lot of what we're seeing in the market is the training models that are being deployed, the large language models, but that's, starting to move to inference as well. So let's talk about the use cases for and the applications. And there's really two primary verticals, and I'll go through these a little bit in the healthcare space and in the financial space. And this is some information from NVIDIA as well. They did a nice job of summarizing the use cases. And there really is a few primary different applications and use cases. So clinical care, operational efficiency, precision medicine, and drug discovery. And so there's a lot of different enterprise companies that are kind of in this space, obviously. And it's kind of the, so the enterprise companies out there, large enterprise companies, some of them will be looking to and have been deploying networks themselves, right? That they're going to purchase, NVIDIA or other equipment and develop their own network, so they have that internal capability. But we're also seeing the outsourcing model being used. So just like public cloud was many years ago, initially, we also have that, these companies have that option as well now. So besides the big, Amazon, Google, and Microsoft of the world, there's several other companies that have kind of startups, I'll call them, AI cloud service providers that are offering compute as a service to companies like this. So there is kind of that option out there, and it's probably likely going to be a hybrid model like it is today for most companies, enterprise companies, to leverage probably on-prem environments as well as some percentage of the compute through a third party. So if we look at on the financial side, there's several different use cases here, and I'm just going to kind of touch on these fairly quickly, but the same holds true. So underwriting type applications, fraud detection, risk simulations, algorithmic trading, credit card processing applications and things like that, customer service in general with, again, on the finance side, personalization, accurate recommendations and mixing things, and just personal finance. So again, a lot of different applications and a lot of different types of companies that, we're already seeing leverage these tools and these models to help run their business, to help, reduce costs, improve efficiency. And same as on the healthcare side, again, we're seeing, a combination of folks that are, using an on-prem and purchasing and doing their networks themselves, as well as outsourcing it as well. So, especially companies like healthcare and finance, they value, things like security and control are important to them. So having an on-prem environment is pretty important for these folks. So just kind of getting into the market a little bit more, just wanted to highlight this stat from Statista, and really just the AI market as a whole. 142 billion was the estimate mid last year, with a growth rate of over 17% annually through the next several years. So pretty large overall market. So now if we dig into that a little bit more, this is a forecast just for the server shipments, and this is from the 650 group at the end of last year. And really what it talks to, so this is in volume, right, units, and traditionally we've seen the majority of the server volume with usage is on x86. But really here they're highlighting the AI and ML servers, and what's forecasted to grow over the next handful of years is an increase of 40%. So pretty significant growth expected there. Looking at that slightly differently, this is actually for bandwidth expected by those different types of really applications. So we're showing the blue is layer 2, the orange is layer 3, the gray is DCI, and then the yellow is AI. So you can see in terms of the bandwidth by different market and an application here over the next several years, some pretty large growth numbers are expected. 124% being the highest for the AI, and overall 50% growth in terms of bandwidth over the next several years. Another thing we wanted to talk about was one of the things that is different with the AI networks is really I'll call it the reintroduction of InfiniBand, in addition to just Ethernet. And I mean, InfiniBand has been around for a long time, but it's been pretty a small percentage of the market, primarily for HPC applications. But we are seeing that here, and we're going to just to kind of touch on that. A large majority, as I say, are being built today with InfiniBand for the compute side. Currently, InfiniBand has a performance advantage with ultra low latency and is a lossless solution. But both Ethernet and InfiniBand are expected to coexist in this space. And on the side here, it kind of highlight why that is. I mean, this is really representing an example of an AI server or node. And there really is two different types of networks. So it's kind of the front end network and the back end. The front end is really the traditional leaf spine environment, which is expected to be all Ethernet. The back end is really the newer piece that's really has the AI compute fabric, leaf to spine, and that really is expected to be the combination of InfiniBand and Ethernet. So Ethernet is expected to grow, as I mentioned, and really driven by some of the performance enhancements that are currently underway, and the desire to have a multi-source ecosystem in the market. So the mix of these two is really going to depend on various factors, customer specific, and the types of applications that they have there. So taking a look at that, the forecast a little bit more too, just on the switch side for the total AI market. Again, this is from the 650 group at the end of last year, and this is in volume, millions of ports. And you can see this is split out by InfiniBand, Ethernet, both back end and front end. And a couple takeaways here. Obviously, you can see overall it's expected to grow pretty significantly over the next several years, total volume. And you see, InfiniBand was relatively small, but that is growing and is expected to continue to grow overall over the next several years. And then the Ethernet side is really expected to, the overall front end as well as the back end to really increase over the next several years. So with that, I'm going to pass it off to Ryan to take it to the next step.
Thanks, Gary. Appreciate it. So now I'm going to review newer higher bandwidth requirements. So let's start by reviewing what's different about generative AI networks. AI networks support extreme workloads with lots of requests per second and multitasking. AI compute requires faster speeds like 200, 400, and 800 gigs at the server. It also requires higher power, and as Gary was talking about, a combination between InfiniBand and Ethernet network connections. Here's an overview of server speeds before new AI servers became popular. On the left here is the enterprise, and it's NIC card speed, so the network interface card 2024 and beyond, showing in the gray that 25 gig is popular and will continue to be popular. On the right is cloud network interface card speeds 2024 and beyond, showing lots of 100 gig and also 200 gig. However, as we know, server speeds for AI are faster. The faster server speeds are enabled by faster network speeds. So here's a forecast for the front end, 2024, 2025, showing the switch to switch connections at 200 gig, 400 gig, and 800 gig with a little 1.6 terabytes in 2025. Then the back end is a little faster in 2024 and 2025. There's going to be a lot of 400 and 800 gig with more 1.6 terabytes in 2025 than the front end. Again, the faster network speeds enable faster servers that support emerging applications. So it went from 10 gig, 25 gig, and the applications that it supports to 100 gig in breakouts and the applications that support. And then now we have 200 and 400 gig that supports GPUs, model training, video at the edge, then also 800 gig server connections that support applications like video model training, HPC, and quantum computing. The exponential jump is accomplished with double the bits in the signal. For example, on the left, NRZ has 2-bit options in the signal. It has zeros and ones used for 10 gig and 25 gig per lane. Now we have PAM4, which is on the right, with 4-bit options in the signal, 00, 01, 10, and 11, used in higher speeds of 50 gigs per lane, and then also 100 gigs per lane. In addition to double the bits, frequency also helps deliver more bits faster. For example, on the top, we have NRZ that delivers 1 bit per baud, and PAM450 delivers 2 bits per baud with the same frequency as NRZ, versus PAM4100 that delivers 2 bits per baud at double the frequency. So again, what you see here at the top is 1 bit for the 25 gigabauds. Then for PAM450, it's 2 bits for 26 gigabauds. And then PAM4100 is the same 2 bits, but double the frequency, 53 gigabauds. The next generation server ports also have double the lanes. For example, single lane, the SFP connectors support 10 gig up to 100 gig with an increase in signal speed that's shown here on the left. Now we also have double lane SFP DD that has a second row of contacts to double the lanes, and it supports 100 gig up to 200 gig and can also be used as breakouts to 2 SFPs. Here is 4-lane quad SFP that supports 40 gig up to 400 gig. It can also be used as breakouts to 4 SFPs or a breakout to half-loaded QSFPs on the server side. So that's what I'm showing here on the right. You see a QSFP that has 4 lanes that's breaking out to 2 QSFPs that are half-loaded. And this is actually becoming really popular in AI systems, the half-loaded connectors. Next, we have 8-lane. On the left is quad SFP double density, also known as QSFP DD, that supports 400 up to 800. It has short contacts and longer contacts to double the lanes. On the right, we have OSFP, and OSFP has a couple of different connector options. There's the finned that's used on the switch end, and that's what I'm showing here on the top. It has a finned heatsink. And then there's also the writing heatsink on the server end, which doesn't have a heatsink on the connector. It actually uses the heatsink from the cage that it plugs into. Also, these OSFP RHS on the server end are typically half loaded, meaning that it has 8 lanes, but typically only 4 lanes are used. The OSFP will not connect into the QSFP DD ports. However, there are hybrid cables and breakout options to help connect equipment with different connector types. So switches can be either InfiniBand or Ethernet. Ethernet AI switches use RDMA over converged Ethernet, which is basically just Ethernet or InfiniBand over Ethernet using InfiniBand packets with compatible Ethernet headers. And the vendors for Ethernet switches for AI systems are Juniper, Cisco, Huawei, Arista, and then also NVIDIA that does both Ethernet and also InfiniBand. The switches connect to server smart NICs, and the vendors for 100 gig and 200 gig speeds are Broadcom, Intel, NVIDIA, AMD, and also Marvell. Also on the server end, there can be faster accelerator cards that offload tasks from the servers, like security functionalities. And today, for speeds above 200 gig, it's primarily NVIDIA with their Bluefield and ConnectX 7. So AI servers support multiple GPUs, NIC cards, and power supplies, more than the typical server does. The server vendors are all the ones that you would expect: Dell, Supermicro, NVIDIA, HPE, Huawei, IBM, and Lenovo. And inside of these servers are GPUs that are with vendors like NVIDIA, which is the leader, Intel, AMD, that also have a nice GPU product set as well. There's lots of options to consider when you're deploying AI systems. So the AI journey starts with an idea, followed by experimentation with some online or cloud tools, and training with, say just a couple of servers to start your training process. Then training at scale, where you deploy lots of AI servers. And then you accomplish inferencing at the edge. However, not all workloads are the same. For example, training tasks takes more compute than inferencing, but it's a balance. It's important to deploy the right amount of compute so it doesn't sit idle. When planning an AI deployment, it can be either on-premise or cloud-based. To help narrow down choices, consider, where is the data? Is the data in on-premise at your location, or is it in the cloud? Also, where are you in the journey and what's next? For example, are you currently training or are you inferencing? The best approach is a balanced hybrid system with a combination of cloud and on-premise. So now I'm going to hand it over to Gary. Hopefully that was informative.
Thank you, Ryan. Excellent. So, all right, continuing on now, talking a little bit about some of the higher bandwidth requirements. Oh, I'm sorry. No, that's what you just covered. Here we are on the network considerations and the DC designs. So I wanted to introduce the some of the terminology, I guess, that in the market. And for those of you not familiar with it, something called reference architectures. So many of the leading hardware vendors that Ryan highlighted there have developed these reference architectures really to provide guidance to users and really providing best practice for installing and deploying these networks. And so we are seeing that quite a bit. Here's some of the benefits that they state that there is, reducing complexity and kind of giving end users and enterprise companies a clear roadmap for the deployment. So these are, guidelines really though, and can be tailored to an organization's specific needs. So you don't necessarily have to follow exactly per the reference architecture. We've seen that already working with several customers in their design and deployments. There's flexibility there definitely. So if we look at a typical kind of architecture design, kind of what does that look like? So I'll kind of talk to that a little bit. There can be 4 separate networks. So initially there's a compute network that we've been talking about, typically InfiniBand or Ethernet, as we mentioned, and at the speeds that we're seeing primarily in the 200, 400 gig, with Ethernet, 100, 200 or 400. Then there's typically storage fabric as well. That's typically 100 gig or 400 gig Ethernet for that network. There's in-band management, also 100 or 400 gig Ethernet. And then there's out-of-band management, typically 1 gig. Okay. So just kind of going back, I want to give a couple of examples of some of the GPUs and the NVIDIA products as an example, what's out there. As Ryan highlighted, one of the market leaders they are definitely today. So this is their DGX A100 server with their GPU. This was released, you can see there a few years ago now. Has been pretty popular in the market though the last couple of years. 100 or 200 gig connection, so InfiniBand or Ethernet. You can see on the back here a couple key points. One is that this requires 8 connections typically of 100 or 200 gig per port, with QSFP56s. So again, pretty high bandwidth as Ryan was talking about. And the power, this is really one of the key points that I wanted to highlight. As Ryan said, that was one of the big factors here and the challenges. So this example, this is 6.5K per box, so for 6U server. So that's quite high. If you look at the average, typically in the market has been called 5 to 15 kW per cabinet. So this is 6.5 kW for one server. So what this has really done, and it's really forced a lot of operators and enterprise companies to really totally change their design of their data center, having to spread things out more than they typically would to be able to handle the cooling for these power requirements. So one is spreading things out and also looking at different ways of cooling, right? Whether it's just straight air cooled, liquid to chip technology, as well as immersion cooling to try to increase the density for these applications. Another example is NVIDIA's H100. Again, that's a little over 2 years ago now, was introduced, but this is also, they've shipped a lot of these GPUs over the last year, and this really moved to the 400 gig capability. Also has can also have 8 400 gig connection, and this is using a different form factor. The one that Ryan mentioned was the OSFP. 11 kW power for this one box. So again, pretty extreme with this, and because of that, you're limited, as I mentioned, in an air-cooled environment to maybe only doing, 2 to 3 of these per cabinet. So next, I want to kind of give some examples of those reference architectures. So I used NVIDIA, and I've got a couple others here. So this is what they call their base pod architecture for the A100. So this is designed up to 10 nodes, and it's really targeted at enterprise customers. Starts with 2 or 4 nodes. It does work with a third-party storage partner versus just NVIDIA. And this is really, can be IB or Rocky in the compute side. That's kind of one option. Then it kind of goes up to their super pod, and this is for the A100. And this is an example I'm showing here. So really, they've created a, it's basically a pod. So it's called a pod, but they call it a scalable unit. So in this case, you've got 20 nodes, 5 compute cabinets. You can see four servers per cabinet with 1 network cabinet between those. And what this allows customers to do is scale, right, and add more and more of these as needed, in groups of these 6 cabinets, so that and then they need to interconnect all of those scalable units together to create one big supercomputer is really what is being done. The other example is their SuperPod with the H100, also designed for 128 plus. In this example, you can see, kind of a 400 gig design, 32 nodes in this example, and using 8 compute cabinets with 2 network cabinets. Again, this would be scaled out and with multiple different nodes. So I wanted to just show another view of what that might look like for 128 node, just a compute cluster. And really, I like this diagram to highlight the complexity that is involved here. If you down at the bottom here are the servers, the H100 examples that I just mentioned, and the scalable units going to leaf switches, to spine switches, to core switches, and you can just see the amount of complexity and the number of connections and the amount of connections that are required in between all of the equipment. It can get fairly complex. Another example I wanted to share of a reference architecture. This is for the Intel side. So again, as Ryan mentioned, 3 primary GPU manufacturers today. So this is the Intel Gaudi 2, and they have what they call a megapod. So this is a smaller 3 cabinet pod, and this can be scaled, smaller to larger. But this is using Rocky, right, for the compute fabric. They recommend and highlight the Supermicro servers and Arista switches. So these are 7060 DX4 switches in this design. So you can see 8 servers with 3 switches per pod. And as Intel highlights, because of the proximity of this, you can use copper DACs in this particular type of a design, because those server to leaf connections are quite a bit shorter than when you spread things out on some of the SuperPod designs. So this is just an example of a design that we actually did for a particular customer and their deployment. And I just kind of want to highlight, so in this case, this was there's really different options for cabling, right? There's a point-to-point, which has been really traditionally done for high-speed HPC networks, or structured cabling. And the reality is, in many cases, it's likely going to be a combination of those two for a hybrid design. As folks that have been around the structured cabling industry for many years, like myself and others, that there are many benefits. That's why to using structured cabling. That's why it is pretty much the standard, de facto standard in most data centers. So we're seeing kind of it makes sense for a hybrid design. In this case, I'm showing 5 compute cabinets, 4 nodes per cabinet, doing a point-to-point just for the server to leaf connections here, and then structured cabling between the cabinets. So this is just referencing other network cabinets in a larger node deployment, a larger cluster. And because each of these pods will look the same as this, but they need to be interconnected. And there's a lot of cabling that needs to be done between those for all the leaf switches going to every spine switch. So I just wanted to give you that type of example, and there's many different ways to skin this in terms of the application, but here's one example. Another example I just wanted to highlight, Ryan was talking about the inferencing as well. So this is looking at, inferencing, which is using, a little bit lower speeds and 100 gig in this example. So with that, you're able to have some more density on the servers. And I'm showing an example here using a Cisco 9K switch with 100 gig downlinks to these servers. And you can easily use a QSFP28 DAC for this application. So really just kind of starting to wrap things up a little bit. I wanted to summarize that really, Siemon has a full solution of AI ready on the fiber cabling solution specifically. We've expanded that offering to really accommodate the newer applications, some of these being using APC connectors and multi-mode environment, which hasn't been common in the past. We've also added different and additional fiber counts in the trunks, which really line up specifically with the node port counts as well as the switch port counts. Things like conversion cords, if as Ryan mentioned as well, in terms of doing breakout. That's basically what this is with on the fiber side, is going up here from let's say a 400 gig switch port to 200 gigs. Not easy to say at the node. So as well as ultra low loss connectivity, which is important for the the latency. In addition to that, Brian, you want to go ahead and highlight and close it out, please?
Sure. So there's lots of cabling options to enable rapid AI deployments with a variety of connector types, which I show here on the top: SFP, SFP-DD, QSFP, QSFP-DD, and OSFP connector types. There's also different network standard types, Ethernet, and also InfiniBand. Also, there's a lot of innovation happening as well with these cable assemblies. For example, gearbox cables for backwards compatibility with PAM 450 to PAM 4100 connections. And also on the copper side, flexible 8-lane passive copper cable constructions are also innovating to be more flexible. And all of these solutions are all tested to make a reliable network connection. Next slide, please. So in summary, today we reviewed the AI market forecast. Also, we dived into AI network details and AI system requirements for power that's making a lot of change in the way people deploy AI and server networks, and also increased speeds as well. Also, we reviewed some reference architectures and gave some examples with different vendors and also different network standards types. There's a lot of change happening, and it's important to understand all your options when making a change, and the Siemon company is here to help. Next slide, please. So, that's all I have today. If there's any questions, please let us know, and we'd be more than happy to answer them now.
All right, guys. Well, thanks. Great job. Yeah, we did actually get a few questions submitted. The first one is for you, Gary. The question was phrased: is single mode or multi-mode fiber cabling typically used in the networks that you talked about today?
So thank you, Brian. That is a good question. So it really is a combination, what we've seen of multi-mode and single mode. So multi-mode has been used for some of the smaller deployments. Typically for these applications is going up to 50 meters for using multi-mode. That can be the server to leaf, but also between the leaf and the spine. But in addition, it's really a combination. We're seeing single mode as well for a larger deployment, probably maybe not for the server to leaf connections, but between the leafs and the spine, the switch-to-switch connections using single mode. So the multi-mode is using, as I mentioned briefly, APC connections for actually that's for 400 gig and above. The 200 gig is still a UPC. So it is a combination of both so far.
All right. Thank you, Gary. The next question was for you, Ryan, and it goes, are FIND OSFP and OSFP RAHS the only OSFP connector types?
That's a good question. There are several options, and the two that I showed, the fin topped, which is for the switch side, has a fin heatsink, is really popular. And then also the OSFP RHS, the writing heatsink, is also really popular on the server end, but there are more options for OSFP. There's the OSFP with the flat top heatsink, which is similar to the FIND, but it has a flat top. And then there's also OSFP XD, which is used for faster speeds. And so all of these are a little different. And so the two that I reviewed are the most popular, the OSFP FIND and the OSFP RHS for the server end.
Okay. All right, guys, and just one more question that I see here is for both you. The question is there any difference in cabling required for InfiniBand or Ethernet networks? And Ryan, I'll go to you first.
So from a DAC and AOC perspective, when you're making a connection for Rocky, which would be an InfiniBand over Ethernet connection, you'd be using an Ethernet cable. If you're making an InfiniBand to InfiniBand connection, it would be an InfiniBand cable. And if you're making an Ethernet to Ethernet connection, it would be Ethernet. But again, a Rocky, which is basically a standard for InfiniBand over Ethernet, it would be an Ethernet cable. Hopefully that answered the question.
Any comments from you, Gary?
Yeah, no, thanks. Yeah, I'll just address that on the fiber cabling side. The reality is with fiber cabling, it doesn't really matter actually. So it is the same cabling, whether it is InfiniBand or Rocky Ethernet. So the same cabling, whether it's single mode or multi-mode, as I mentioned, would be used.
Excellent. All right, guys. Well, that's all the questions that I see that got submitted. So I'll just send us out here. So before we close today's session, I'd like to say a huge thank you to you all for joining us and to Gary and Ryan for their time and excellent insights. We hope you found the session interesting and look forward to seeing you at other Cloud Evolution sessions throughout the coming months. Please head to siemon.com/cloudevo to register your place. If you have any questions or would like any additional information on how Siemon can support your data center projects, please reach out to Gary or Ryan directly or contact your local Siemon representative. Thanks again, everyone, and take care.
Thank you all. Take care. Thank you for